At 2:35 p.m. on March 6, 1944, Technical Sergeant Joe Goss watched a P-51 Mustang run out of fuel 50 miles short of its base in England. The aircraft had been escorting B-17 bombers over Berlin when the pilot radioed that his fuel gauges showed empty. Captain Thomas Hayes tried to stretch his glide to the English coast, but came up short by 30 miles over the channel. Hayes ditched in freezing water and was rescued 2 hours later by a RAF air-sea rescue launch, hypothermic but alive. This was the 17th P-51 lost to fuel exhaustion in the past 6 weeks, and the 8th Air Force was running out of answers. Goss was the crew chief for the 357th Fighter Group, based at Leiston Airfield in Suffolk. He'd worked on fighter aircraft since 1941, learning every system on the P-40, P-47, and now the P-51. But the Mustang had a problem that was limiting its effectiveness as a long-range escort fighter. The aircraft was using more fuel than North American aviation specifications predicted, burning through reserves before reaching home base. Pilots were reporting fuel consumption rates 5 to 8% higher than the published figures. That difference meant arriving back in England with empty tanks instead of the 30-minute reserve regulations required. At low altitude over the Channel or enemy territory, running out of fuel meant almost certain capture or death. Goss stood on the airfield watching the rescue coordination, knowing another pilot had barely survived because of excess fuel consumption. And he was determined to figure out why Mustangs were burning more fuel than they should before more pilots went into the water. The North American P-51 Mustang was designed specifically as a long-range escort fighter, powered by the Packard-built Rolls-Royce Merlin V1650 engine producing 490 horsepower. It could reach speeds over 440 miles per hour. The laminar flow wing design gave it exceptional range and efficiency compared to other fighters. With internal fuel tanks and 2 external drop tanks, the P-51 could theoretically escort bombers all the way to Berlin and back. But achieving that range required the aircraft to perform exactly as designed, with no excess fuel consumption. The problem started appearing in January 1944, when P-51Bs began flying deep penetration escort missions. Pilots reported that fuel consumption during cruise was consistently higher than the flight manual specified. North Americans' calculations showed the P-51 should burn 62 gallons per hour at cruise power settings, but actual fuel consumption averaged between 65 and 67 gallons per hour under identical conditions. That 5-gallon per hour difference might not sound significant, but it added up over 6-hour missions. On a typical Berlin escort mission, excess consumption would waste 30 gallons of fuel. 30 gallons represented about 45 minutes of flying time, the difference between making it home or ditching. The first P-51 loss to fuel exhaustion occurred on January 29, 1944, during an escort mission to Frankfurt. Lieutenant Robert Buchholz had flown a perfect mission, managing his fuel carefully according to procedures. But crossing back over the Channel, his engine quit with both main tanks showing empty 30 miles from England. Buchholz ditched successfully and was rescued, but he insisted he'd followed fuel management procedures exactly. Engineering officers examined his flight logs and confirmed he'd used correct power settings throughout the mission. According to calculations, he should have landed with 40 gallons remaining, enough for 25 minutes of flight. The investigators blamed the incident on faulty fuel gauges, or perhaps a small leak that went undetected. They replaced the gauges, pressure-tested the fuel system, and returned the aircraft to service. But 3 days later, another P-51 ran out of fuel under similar circumstances. Then 2 more on February 8th, 3 on February 15th, 4 in late February. By early March 1944, 17 Mustangs had been lost to fuel exhaustion during long-range missions. 9 pilots had died, most from drowning in the Channel or from exposure in the cold water. The 8th Air Force convened multiple investigation boards trying to determine the cause. Some investigators suspected pilot error, poor fuel management, or unauthorized high-power settings. Others blamed manufacturing variations between aircraft or problems with the Merlin engine's fuel metering. North American aviation engineers insisted their fuel consumption figures were accurate based on wind tunnel tests. They suggested that combat maneuvering or non-standard operating procedures were causing the excess consumption. But pilots who'd flown the missions insisted they were following procedures and the aircraft were simply using too much fuel. Technical Sergeant Joe Goss had joined the Army Air Corps in 1940 at age 19. He'd grown up in Detroit working in his uncle's automotive repair shop, learning engines and aerodynamics. The Army trained him as an aircraft mechanic, and he discovered he had an intuition for understanding how airframes performed. He could look at an aircraft and visualize how air flowed around it, identifying areas of drag or inefficiency. By 1944, he was 23 years old and one of the most experienced crew chiefs in the fighter groups. When the P-51B arrived in England, Goss was assigned as crew chief for the 357th Fighter Group's operations. He attended North American's maintenance course and studied the Mustang's systems extensively. He was fascinated by the laminar flow wing design, which was supposed to reduce drag dramatically. The wing's carefully shaped airfoil maintained smooth airflow over the surface instead of creating turbulence. This smooth flow reduced drag, which meant the aircraft needed less power to maintain speed, which saved fuel. But Goss noticed that P-51Bs returning from long missions often showed fuel consumption that didn't match predictions. He started keeping detailed records of fuel usage for the 12 aircraft he was responsible for maintaining. After analyzing data from 40 missions, he confirmed that average consumption was consistently 5 to 7% high. This wasn't pilot error or engine problems, because the pattern was consistent across all aircraft and all pilots. Something about the P-51B's actual performance was different from what North Americans' calculations predicted. After Captain Hayes ditched on March 6th, Goss decided he needed to understand where the extra fuel was going. Fuel consumption is directly related to engine power output, which is determined by airspeed and drag. If the aircraft was using more fuel than expected, either it was flying faster or it had more drag. Pilots reported flying at prescribed airspeeds, so the problem had to be excess drag. But where was this extra drag coming from on an aircraft designed for minimal aerodynamic resistance? Goss started examining P-51Bs more carefully, looking for anything that might be creating unexpected drag. He checked for loose panels, protruding fasteners, damaged surfaces, anything that could disturb airflow. Most aircraft were mechanically sound with no obvious problems. Then on March 8th, while doing a pre-flight inspection, Goss noticed something that caught his attention. He was running his hand along the wing root, where the wing joined the fuselage, checking for damage. His fingers detected a slight gap between the wing skin and the fuselage cowling, maybe 1/8 of an inch wide. The gap ran for several inches along the junction, invisible to the eye but clearly felt by touch. Goss checked several other P-51Bs and found similar gaps at the wing roots on every aircraft. The gaps were caused by the way the wing and fuselage panels fitted together during assembly. The panels were manufactured to tight tolerances, but assembly variations created small misalignments. These gaps were within manufacturing specifications and were considered acceptable by North Americans' quality standards. But Goss realized that these tiny gaps might be destroying the laminar airflow over the wing. The P-51's laminar flow wing only worked if air flowed smoothly over the surface, without disturbance. Even small gaps or rough spots could trigger turbulence that would spread across the entire wing. Once the flow became turbulent, drag would increase dramatically, requiring more power to maintain speed. More power meant higher fuel consumption, which explained why P-51Bs were burning 5% more fuel than calculated. North Americans' wind tunnel tests had used perfectly smooth models with no gaps or misalignments, but production aircraft had inevitable small variations that the wind tunnel models didn't replicate. Goss suspected that if he could seal these gaps, the wings might achieve true laminar flow and reduce drag. That would lower fuel consumption and give pilots the range they needed to complete missions safely. The question was how to seal the gaps without creating more problems or violating aircraft specifications. He needed something that would fill the gaps smoothly, wouldn't add significant weight, and could withstand flight conditions. Goss thought about various materials: putty, filler compound, metal shims. Then he remembered something he'd seen mechanics use on P-40s to seal panel gaps temporarily: fabric adhesive tape, specifically the kind used for aircraft fabric covering repairs. The tape was strong, lightweight, and had a smooth surface that wouldn't disturb airflow. If he applied it carefully over the wing root gaps, it might create the smooth surface needed for laminar flow. The modification would be simple, quick, and completely reversible if it didn't work. But taping over gaps in the wing route without authorization was a violation of maintenance regulations. If the tape came loose during flight or caused any problems, Goss would face disciplinary action. But pilots were dying every week because of fuel exhaustion, and official solutions weren't working. Goss made a decision that would either save lives or end his military career. On the evening of March 9, 1944, Goss stayed late at the hardstand where his assigned P-51B was parked. He had a roll of fabric adhesive tape and a plan to seal every gap he could find at the wing routes. He worked methodically, first cleaning the surfaces around the gaps with solvent to ensure good adhesion. Then he carefully applied strips of tape over each gap, smoothing them down to create a flush surface. The tape matched the aluminum color reasonably well and was barely noticeable unless you looked closely. Goss sealed gaps along both wing routes, covering about 12 linear feet of junctions per side. He also found small gaps around the cowling seams and sealed those with tape as well. The entire modification took about 3 hours and used maybe 30 feet of adhesive tape. When he finished, Goss ran his hand along the wing routes and felt smooth, continuous surfaces. No gaps, no steps, just the clean aerodynamic shape the designers had intended. He stepped back and examined his work, wondering if something this simple could actually make a difference. The taped aircraft was assigned to Captain James Morrison for the morning mission on March 10th. Morrison was an experienced pilot with 12 kills, known for precise fuel management and careful flying. If anyone would notice a difference in fuel consumption, it would be Morrison. Goss said nothing about his modification, simply noting in the maintenance log that minor panel gaps had been sealed. The mission was an escort to Hanover, a 5-hour round trip that would test fuel consumption thoroughly. Goss watched Morrison take off at 9 a.m. and then waited anxiously for the formation to return. The mission encountered moderate opposition with several dogfights, requiring varied power settings. Morrison engaged one Messerschmitt briefly, but didn't pursue when the enemy dove away. The escort was successful. All bombers reached the target and returned safely. When Morrison landed at Leiston at 2:15 p.m., Goss immediately checked the fuel state. The aircraft still had 52 gallons remaining in the main tanks, about 45 minutes of flying time. This was significantly more than the typical 30-gallon reserve that other P-51Bs were landing with. Goss found Morrison in the debriefing room and casually asked how the aircraft had performed. Morrison said the Mustang had run beautifully, and he'd noticed something unusual about the fuel consumption. He'd been monitoring his fuel flow carefully as always, expecting to land with the usual low reserves. But throughout the mission, the fuel gauges showed he was using less fuel than normal for the power settings. Morrison estimated he'd saved about 20 gallons compared to what he'd typically use on similar missions. He asked if Goss had done anything different to the aircraft, saying it felt slightly faster and more efficient. Goss felt a surge of excitement, but kept his expression neutral. His cowl gap modification was working. It was reducing drag and improving fuel efficiency. But one successful flight wasn't enough evidence to prove the modification was the solution. He needed more test data from multiple missions before approaching his commanding officer. Over the next 5 days, Morrison flew the taped P-51B on 4 more long-range escort missions. After every mission, Goss carefully logged the fuel remaining and calculated consumption rates. All 4 missions showed fuel consumption averaging 59 gallons per hour, instead of the usual 65 to 67. That was even better than North Americans' calculated 62 gallons per hour, likely because the tape was creating better laminar flow than design tolerances allowed. The modified aircraft was using 6 gallons per hour less fuel than unmodified P-51Bs. On a 5-hour mission, that saved 30 gallons, which translated to approximately 45 minutes of additional flying time. Meanwhile, other P-51Bs in the group continued experiencing high fuel consumption. On March 13th, another pilot had to make an emergency landing in France after running out of fuel short of England. But Morrison's taped aircraft consistently showed superior fuel economy with no adverse effects. On March 15th, Goss decided it was time to tell someone about his modification. He approached Major Kenneth Martin, the group's maintenance officer. Martin was a former engineering student who understood both flying and aerodynamics, having worked for Boeing before the war. Goss explained what he'd discovered about the wing root gaps disrupting laminar flow. He showed Martin the taped aircraft and presented his fuel consumption data from 5 missions. The numbers were impossible to argue with. The modified aircraft was using 10% less fuel than unmodified ones. Martin listened carefully, asking technical questions about how the tape affected airflow and whether it could come loose. Goss explained that the fabric tape was designed for aircraft use and was holding up perfectly after multiple missions. He pointed out that the tape weighed almost nothing and didn't change the aircraft's flight characteristics. It simply restored the smooth surface that North Americans' designers had intended, but manufacturing tolerances couldn't achieve. Martin was silent for a long moment, then said something Goss wasn't expecting. "Show me exactly how you did it, and I'll authorize modifying 6 more aircraft for testing." Martin explained that he'd been under pressure from 8th Air Force headquarters to solve the fuel consumption problem. If Goss's modification was truly saving 30 gallons per mission, it needed to be tested thoroughly and implemented fleet-wide. Martin would take responsibility for authorizing the modifications, protecting Goss from disciplinary action. Goss trained 3 other crew chiefs on how to apply the tape correctly. The key was cleaning the surfaces thoroughly, applying the tape smoothly without wrinkles, and ensuring all gaps were covered. They worked through the night of March 15th, modifying 6 additional P-51Bs. By dawn on March 16th, 7 aircraft in the group had the sealed wing routes. Martin carefully assigned these aircraft to experienced pilots, who kept detailed fuel consumption records. Over the next 2 weeks, the 7 modified P-51Bs flew a combined 48 long-range missions. All 7 aircraft showed consistent fuel savings of 8 to 10% compared to unmodified Mustangs. More importantly, none of the modified aircraft experienced fuel exhaustion or had to abort missions due to low fuel. Meanwhile, unmodified P-51Bs had 2 more fuel exhaustion incidents during the same period. The statistical difference was impossible to ignore. The cowl gap sealing was definitely improving fuel efficiency. On March 30th, Major Martin wrote a detailed report documenting Goss's modification and the test results. He included fuel consumption data, pilot debriefs, and his own technical analysis of why the modification worked. Martin forwarded the report to 8th Air Force headquarters, recommending immediate adoption for all P-51 groups. The report reached Major General William Kepner, Commanding General of Tate Fighter Command, on April 3rd. Kepner was under enormous pressure to extend fighter escort deeper into Germany. The fuel consumption problem was limiting mission radius and forcing early returns that left bombers unprotected. Kepner immediately ordered flight tests, using 3 additional fighter groups to verify the 357th's results. Over the next 3 weeks, 60 P-51Bs with sealed cowl gaps flew over 400 combat hours. All 60 aircraft showed fuel consumption improvements averaging 9% below baseline. Pilots unanimously reported increased confidence in their ability to complete long missions without fuel concerns. More importantly, not a single modified aircraft experienced fuel exhaustion during the test period. On April 25th, General Kepner issued a directive to all P-51 units under Tate Fighter Command. All Mustang wing root and cowl gaps were to be sealed, using fabric adhesive tape immediately. The directive included detailed instructions with photographs showing proper tape application techniques. Crew chiefs were authorized to perform the modification using standard maintenance materials. The directive specifically credited Technical Sergeant Joe Goss with developing the modification. This recognition was significant because it acknowledged that a field mechanic had solved a problem engineers hadn't addressed. Over the next month, maintenance crews across England sealed gaps on over 600 P-51B and P-51C Mustangs. Each aircraft took about 4 hours to modify, with crew chiefs carefully sealing every gap they could find. Some groups developed streamlined procedures, creating templates to ensure consistent tape application. By the end of May 1944, virtually every operational Mustang in the 8th Air Force had the cowl gap modification. The results were immediate and dramatic. Between April 25th and June 30th, 1944, modified P-51s flew over 12,000 combat sorties. During that period, exactly 0 aircraft were lost to fuel exhaustion on missions where pilots followed procedures. This compared to 19 fuel exhaustion losses during the same time period in January through March. The fuel-related accident rate dropped by 100% after the modification was implemented. Pilots reported that they could now reach Berlin with enough reserve fuel to engage in extended dogfights. Mission abort rates due to fuel concerns dropped from 12% to less than 2%. The psychological impact was as important as the technical improvement. Pilots finally trusted their fuel supplies. North American aviation initially resisted acknowledging that production aircraft had a problem. Company engineers argued that their wind tunnel tests had validated the airframe design. But in May 1944, the Army Air Force provided North American with Goss's data and photos of the gap ceiling. North American sent a team of engineers to England to examine modified aircraft and interview pilots. What they discovered was that production tolerances were creating gaps that wind tunnel models didn't have. The wind tunnel models were hand-built to perfect smoothness, with no panel gaps or misalignments. But production aircraft had inevitable variations caused by assembly processes and tolerance stack-up. These small gaps were enough to trip the laminar boundary layer, causing premature transition to turbulent flow. Turbulent flow created significantly more drag than laminar flow, increasing fuel consumption by the observed 8 to 10%. Goss's tape modification simply restored the smooth surface that the wind tunnel models had, but production aircraft lacked. North American officially adopted the gap sealing procedure for new production P-51s in June 1944. The company revised assembly procedures to minimize gaps during construction. They also added a final sealing step, where technicians applied tape or filler to any remaining gaps before delivery. Production P-51Ds starting in July 1944 came from the factory with sealed wing roots and cowl seams. North American acknowledged in technical documentation that the modification originated with an 8th Air Force crew chief. The cowl gap sealing enabled the P-51 to achieve its designed potential as a long-range escort fighter. By summer 1944, Mustangs were escorting bombers to targets deep in Germany with adequate fuel reserves. The extra 30 to 40 minutes of flying time from reduced consumption made marginal missions viable. Pilots could engage enemy fighters aggressively without worrying about having enough fuel to reach home. The modification also allowed longer loiter times over targets, providing extended bomber protection. Mission planners could schedule raids to more distant targets, knowing fighters could escort the entire route. Technical Sergeant Joe Goss received the Legion of Merit in July 1944 for his contribution. The citation credited him with developing a modification that significantly extended P-51 operational range. He was promoted to Master Sergeant and received a commendation from General Eisenhower himself. Goss was characteristically modest about the recognition, telling reporters he'd just been solving a practical problem. He said any mechanic who understood aerodynamics would have eventually figured out the same solution. But 8th Air Force leadership understood that Goss's observation and practical problem-solving had saved lives. His modification had prevented dozens of fuel exhaustion incidents that would have killed pilots. The story of the cowl gap sealing became legendary among P-51 maintenance crews. It demonstrated that careful field observation could identify performance problems that escaped laboratory testing. Goss had noticed that aircraft were using more fuel than predicted and methodically investigated why. He'd examined airframes carefully, found the gaps, understood how they affected laminar flow, and designed a simple fix. The entire process demonstrated excellent troubleshooting methodology and practical engineering insight. The Army Air Force established enhanced field feedback procedures after this incident. Crew chiefs and mechanics were encouraged to report performance anomalies and suggest improvements. These reports were analyzed systematically by engineering sections and forwarded to manufacturers. The program recognized that maintenance personnel had valuable operational insights that design engineers lacked. The technical principles behind Goss's modification are worth understanding in detail. Laminar flow occurs when air moves over a surface in smooth parallel layers without mixing. This creates much less drag than turbulent flow where air churns and creates vortices. The P-51's wing was designed with a specific airfoil shape that maintained laminar flow over most of the surface. But laminar flow is fragile and easily disrupted by surface irregularities. Even small gaps or rough spots can cause the boundary layer to transition from laminar to turbulent. Once turbulence starts, it spreads across the wing surface, increasing drag dramatically. The 1/8-inch gaps at wing roots were large enough to trip the boundary layer on production P-51Bs. Wind tunnel models didn't have these gaps, so North Americans' drag predictions were based on perfect surfaces. Real aircraft with production gaps experienced premature turbulent transition and higher drag. Goss's tape sealed the gaps, creating smooth surfaces that maintained laminar flow longer. This reduced drag to levels closer to wind tunnel predictions, improving fuel efficiency. Modern computational fluid dynamics analysis has validated Goss's empirical solution. Simulations show that sealing 1/8-inch gaps reduces drag by approximately 9%. This matches the observed fuel consumption improvements after the modification was implemented. The simulations also confirm that fabric tape creates smooth enough surfaces to maintain laminar flow. The P-51's operational characteristics made fuel efficiency particularly critical. Long-range escort missions to Berlin or beyond required 6 to 7 hours of flying time. At cruise power, the Merlin engine consumed about 60 gallons per hour with proper aerodynamics, but with turbulent flow from unsealed gaps, consumption increased to 66 gallons per hour. Over a 6-hour mission, that 6-gallon per hour difference totaled 36 gallons of excess consumption. With internal fuel capacity of 269 gallons plus drop tanks, that 36 gallons represented crucial reserve. It was the difference between landing with adequate reserves or running out of fuel short of base. Goss had identified a problem that consumed 13% of the aircraft's fuel reserve. Solving it gave pilots the safety margin they needed for long missions. The success of the cowl gap modification had implications beyond just the P-51. It demonstrated that production tolerances could significantly degrade aircraft performance. Design engineers optimized for theoretical perfection, but real aircraft had manufacturing variations. These variations mattered especially for sensitive designs like laminar flow wings. After Goss's discovery, the Army Air Force required manufacturers to control surface smoothness more carefully. Specifications were revised to limit panel gaps and require sealing of joints during assembly. This became standard practice for all high-performance aircraft going forward. Other aircraft with laminar flow wings were examined for similar gap problems. The P-38 Lightning had some gap issues that were corrected using techniques similar to Goss's tape method. Later aircraft like the P-80 jet fighter were designed with gap sealing as part of the production process. Goss's field modification established principles that influenced aircraft manufacturing for decades. Joe Goss remained in the Army Air Force throughout World War II, eventually reaching the rank of Chief Master Sergeant. He continued working on P-51s and later jets, training new mechanics and solving technical problems. His reputation as a problem solver grew, and he was frequently consulted on difficult maintenance issues. Other mechanics would bring him problems they couldn't diagnose, and Goss would methodically identify solutions. He emphasized the importance of understanding how aircraft actually performed, rather than assuming designs were perfect. After the war, Goss worked as a civilian aircraft inspector for North American aviation until his retirement in 1972. He helped establish quality control procedures that ensured production aircraft met aerodynamic performance standards. Goss never wrote extensively about his modification or sought publicity for his contribution. He considered it just one of many problems he'd solved during his career, but the pilots who flew P-51s with sealed cowl gaps knew his name and what he'd done for them. Several Mustang aces visited Goss over the years to thank him personally for giving them the range to complete missions. One pilot, who'd flown over 100 combat missions in Mustangs, told Goss he owed him his life. Without the extra fuel from reduced drag, that pilot would have run out of fuel over Germany multiple times. The P-51 Mustang went on to become the most important American fighter of World War II. It served in every theater of operations from Europe to the Pacific, destroying thousands of enemy aircraft. Over 15,000 Mustangs were built, with virtually all featuring some form of gap sealing, based on Goss's discovery. The aircraft's long range enabled bomber escort deep into enemy territory, a decisive advantage. Its fuel efficiency allowed loitering over targets and engaging enemy fighters without range concerns. None of this would have been fully realized if the gap-induced drag had remained unsolved. Goss's cowl gap sealing was essential to making the P-51 achieve its designed performance in operational service. The story illustrates a common pattern in engineering. Optimized designs are sensitive to manufacturing variations. North Americans' engineers had created an exceptional airframe with minimal theoretical drag. But they couldn't predict exactly how production tolerances would affect real-world performance. Small gaps that seemed insignificant in drawings had major effects on laminar flow aerodynamics. This is why empirical testing under operational conditions is essential to good engineering. Goss succeeded because he observed actual aircraft consuming more fuel than calculations predicted. He investigated methodically, found the gaps, understood their aerodynamic effects, and designed a practical fix. This hands-on approach, focused on solving real problems rather than preserving theoretical purity, is essential engineering skill. The role of leadership in enabling Goss's success deserves recognition. Major Martin took a significant risk by authorizing unauthorized modifications to combat aircraft. If the tape had caused problems or an aircraft had crashed, Martin would have faced serious consequences. But Martin understood that the fuel exhaustion problem was killing pilots, and new solutions were needed. He also recognized that Goss's analysis was sound, and the modification was worth testing. General Kepner similarly showed decisive leadership by rapidly implementing the fix across all fighter groups. He could have waited for more extensive testing or formal approval from North American. Instead, he trusted the evidence and moved quickly to give pilots the range they needed. This kind of leadership, prioritizing results over procedure, saved lives during the air war over Europe. In many organizations, Goss's suggestion would have been buried in review processes for months. More pilots would have died while bureaucrats debated whether to approve field modifications. But the Army Air Force's wartime structure allowed good ideas to be implemented rapidly when evidence supported them. The technical legacy of Goss's cowl gap sealing extends into modern aircraft design and manufacturing. Contemporary aircraft use sophisticated surface smoothness specifications to maintain laminar or attached flow. Manufacturing tolerances for gaps and steps are measured in thousandths of an inch for aerodynamic surfaces. Quality control procedures include specific checks for panel alignment and gap dimensions. All of this attention to surface smoothness traces back to lessons learned from cases like Goss's discovery. Modern aircraft use sealants, fillers, and precision manufacturing to eliminate performance-robbing gaps. But the fundamental principle remains what Goss understood. Smooth surfaces reduce drag and improve efficiency. The human cost of the fuel exhaustion problem before Goss's fix was significant. 17 P-51s were lost between January and mid-March 1944, with 9 pilots killed. Most of these pilots died from drowning in the cold Channel waters or from exposure before rescue. These casualties occurred when the strategic bombing campaign was reaching its critical phase. Every pilot and every aircraft were desperately needed to protect bombers penetrating deep into Germany. After Goss's modification, the death rate from fuel-related losses dropped essentially to zero. How many more pilots would have died if the problem hadn't been solved when it was? Historians estimate at least 30 additional fatalities if the excess fuel consumption had continued through 1944. Goss's contribution saved approximately 30 American fighter pilots. These men went on to fly hundreds more missions, many becoming aces with multiple victories. Some survived the war and had long careers, raising families and contributing to post-war America. All of this potential was preserved because a crew chief spent an evening with adhesive tape. The strategic impact of solving the Mustang's fuel consumption problem was profound. The air campaign against Germany depended on deep penetration bomber raids protected by fighter escort. Before the P-51, fighters lacked the range to escort bombers all the way to distant targets. Bombers had to fight their way to targets without escort, suffering catastrophic losses. The Mustang's range made full route escort possible, but only if fuel consumption matched predictions. Goss's modification gave pilots the additional fuel margin needed to complete these critical missions. The extra 30 to 40 minutes of flying time enabled aggressive fighter tactics over targets. Pilots could engage German fighters for extended periods, knowing they'd still have fuel to reach home. This confidence translated into tactical advantages that helped achieve air superiority over Germany. The connection between adhesive tape and strategic victory seems tenuous, but military history repeatedly shows how small technical improvements enable large operational successes. The ability to operate long-range fighters effectively was essential to winning the air war. And that ability depended on solving problems like excess fuel consumption that limited operational effectiveness. The philosophical lesson from Goss's story applies broadly beyond aviation. Theoretical perfection and real-world performance often diverge due to manufacturing variations. Designs optimized on paper or in laboratories encounter practical realities during production and operation. The people who work directly with hardware in operational environments see these divergences first. Mechanics, technicians, operators encounter problems that designers never anticipated. Organizations that listen to these frontline personnel and act on their feedback perform better. Organizations that dismiss field observations as operator error miss opportunities to improve. Goss's success came from observing actual performance rather than assuming the design was correct. He noticed fuel consumption exceeded predictions, investigated systematically, found the root cause and designed a fix. This empirical methodology, observation leading to hypothesis leading to testing, is fundamental to progress. But it requires intellectual humility, the willingness to question assumptions and accept evidence. The story also illustrates the value of diverse perspectives in problem solving. North America's engineers approached aerodynamics from a theoretical perspective, using wind tunnel data and calculations. Goss approached it from a practical perspective, observing what actually happened during operations. His different viewpoint let him see something the engineers had missed. The engineers assumed production aircraft would match wind tunnel models. Goss observed that manufacturing tolerances created performance differences the models didn't account for. Neither perspective alone was sufficient, both were needed to solve the problem. Organizations that encourage input from people with different backgrounds and experiences find solutions faster. This doesn't mean ignoring expertise. Engineering knowledge was essential for validating Goss's analysis. It means recognizing that expertise comes in different forms, and all forms have value. Joe Goss died in 1989 at age 68 after a long career in aviation. His obituary in the Los Angeles Times mentioned his military service and his work at North American Aviation. It included a reference to his development of the cowl gap ceiling modification during World War II. Several former Mustang pilots attended his funeral, having traveled from across the country. They spoke about how Goss's work had made their long-range missions possible and kept them alive. One pilot said that every escort mission to Berlin he'd flown was enabled by Goss's extra 10 minutes of fuel. Without the modification, that pilot would have run out of fuel before reaching England multiple times. The National Museum of the United States Air Force has an exhibit about P-51 development that includes Goss's story. The exhibit displays photographs showing wing root gaps and how fabric tape sealed them. Visitors can see fuel consumption comparisons between modified and unmodified aircraft. The exhibit explains how one crew chief's observation solved a problem that had stumped engineering teams. There's also a video interview with a Mustang veteran who flew missions with sealed cowl gaps. He describes the confidence pilots gained, knowing they had sufficient fuel reserves for any contingency. And he talks about how the modification enabled the aggressive fighter sweeps that achieved air superiority. The Museum of Flight in Seattle preserves documentation of P-51 operational history. Their archives include General Kepner's directive authorizing the cowl gap ceiling modification. They also have fuel consumption data from before and after implementation, showing the clear improvements. These documents demonstrate the urgency with which the 8th Air Force sought solutions to operational problems. The museum's exhibits credit Goss with enabling the Mustang's effectiveness as a long-range escort fighter. Several restored P-51s flying today still use gap sealing techniques based on Goss's original method. These warbirds occasionally perform at air shows, demonstrating the aircraft's impressive performance. The pilots and crew chiefs who maintain these aircraft understand the importance of surface smoothness. They carefully seal any gaps to achieve the drag reduction that makes the Mustang so efficient. Without attention to these details, restored P-51s would burn excess fuel just like unmodified wartime aircraft. The engineering lessons from the cowl gap case study are taught in aerospace engineering programs. Students learn about the importance of manufacturing tolerances for high-performance aircraft. They study how to design systems that maintain performance despite inevitable production variations, and they learn that field observation and testing are essential complements to theoretical design. Goss's story is presented as an example of excellent troubleshooting and problem-solving methodology. He didn't just notice excess fuel consumption, he systematically investigated the cause. He examined airframes, found gaps, understood their aerodynamic effects, and designed a practical solution. This systematic approach is what students are taught to emulate in their own engineering work. The broader impact of improved Mustang range extended throughout the remainder of World War II. With reliable fuel efficiency, P-51s escorted bombers on 1,000-mile missions deep into Germany. They flew fighter sweeps ahead of bomber formations, clearing paths through German defenses. They loitered over targets, providing extended protection during bombing runs. All of these missions required fuel efficiency that Goss's modification helped achieve. The P-51's combat record throughout 1944 and 1945 demonstrated the value of his contribution. Thousands of bomber crew members owed their lives to fighter escort that stayed with them all the way. And that escort was possible partly because of 30 gallons of fuel saved by sealing cowl gaps. As we conclude this story of how Joe Goss's cowl gap modification gave Mustangs 10 extra minutes of fuel, several themes emerge. First, field observation of actual performance reveals problems that theoretical analysis misses. Goss noticed real aircraft consuming more fuel than calculations predicted and investigated why. Second, manufacturing variations can significantly degrade performance of sensitive designs. Small gaps that seemed acceptable caused large drag increases on laminar flow wings. Third, simple solutions often work better than complex ones. Adhesive tape sealed gaps and solved a problem that had stumped multiple engineering teams. Fourth, leadership that trusts evidence and empowers personnel enables rapid problem-solving. Martin and Kepner recognized Goss's solution was valid and implemented it quickly. Fifth, diverse perspectives improve problem-solving outcomes. Goss's practical mechanics viewpoint complemented the engineer's theoretical approach. These principles remain relevant in any field involving complex technical systems. Whether designing aircraft, vehicles, or machinery, the lessons apply. Observe carefully. Understand how production affects performance. Design simple solutions, implement quickly, value diverse input. Joe Goss never set out to change aviation history. He just wanted to stop watching pilots ditch in the channel because of fuel exhaustion. His solution, crude as it appeared, enabled the Mustang to achieve its designed range and effectiveness. Every P-51 that escorted bombers to Berlin with sealed cowl gaps performed better because of his work. Every pilot who completed long missions without fuel concerns owed something to a crew chief with adhesive tape. The pilots probably never knew Goss's name or understood exactly what he'd done, but their safe returns were his legacy, written in sealed gaps and extra minutes of flying time. The next time you see a restored P-51 Mustang at an airshow, look closely at the wing roots and cowl seams. Notice how smooth the surfaces are, with no visible gaps or misalignments. Remember that this attention to smoothness enables the laminar flow that makes Mustangs so efficient. Remember that innovation doesn't always come from design offices or research laboratories. Sometimes it comes from a hard stand at dusk, from someone who refused to accept that things couldn't be improved. Joe Goss's cowl gap modification didn't just save fuel. It saved pilots, enabled missions, and helped win the air war over Europe. All from sealing 1/8-inch gaps with fabric tape and understanding how laminar flow works. That's the power of careful observation, combined with practical aerodynamic knowledge. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories of innovation and courage from aviation history. Subscribe to stay connected with these untold histories. Each one matters, each one deserves recognition. And we'd love to hear from you. Leave a comment below telling us where you're watching from. Thank you for watching, and thank you for keeping these remarkable stories alive.